right, we're into section 4 of chapter 11 on mathematical induction. Now, mathematical induction is a very useful tool, and it helps you with proving, as the print says, it helps you to prove the validity of a statement that's true over a set of positive integers. You're going to get a lot of this type of proof in college, typically in some kind of like a matrix algebra or an abstract algebra class, but it can even be in calculus. So what we're going to do is we're going to look at the two key components of it, and then we're going to go ahead and we're going to do a couple of examples to show you what's going on. So the idea of mathematical induction is to show that something is true when it starts off for the initial statement. So the principle of mathematical induction says let p sub n be a statement involving the positive integer n and let k be an arbitrary positive integer. Thus, if p sub n is true for all positive integers n, if p sub 1 is true, so that's the initial statement, and the truth of p sub k implies the truth of p sub k plus 1. So if we assume that p sub k is true, then we can go ahead and use that to see if we can show that p sub k plus 1 is true as well. And if we do that, then we have kind of a domino effect, because we'll know that the first one is true, the second one would be based on the first one, the third one would be based on the second, and that's what I tried to write out here. That p sub 1 will be true, then that implies the truth of p sub 2, which implies the truth of p sub 3, and so on down the way. So again, kind of the domino effect. You knock over the first domino, it knocks into the second, into the third, and you knock down the whole string of dominoes. So we'll try a couple of examples. The first one's a little bit easier than the second one. It says use mathematical induction to prove that p sub n, which is the statement here that 2 plus 4 plus 6 plus 8, you're adding up consecutive positive integers here, all the way up to plus 2 sub n, arbitrary, is equal to n times the quantity n plus 1. So the first thing we're going to do is we're going to show that this is true for p sub 1. That's the first part of the proof back here. Remember, we have to show that this is true. Well, p sub 1 means only the first term. So this would mean 2 would equal, and then remember your subscript is 1 here. The conclusion is that it equals n times the quantity n plus 1. Well, for p sub 1, this would be 1 times the quantity 1 plus 1. And of course, that's 1 times 2. Notice still using 1 plus 1 equals 2 after all these years. And then 2 is equal to 2. And that's the true statement. So we verified it for the initial statement. Now, we'll go to, over here, that p sub k implies the truth of p sub k plus 1. What that means in fancy talk is that if p sub k is assumed to be true here, now p sub k, I'm going to just write this out, except I'm going to replace the n's with the k's, and I'd have 2 plus 4 plus 6 plus 8 plus dot 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 plus 2k, and that would equal k times the quantity k plus 1. If this is true, then let's see if it's true for p sub k plus 1. So p sub k plus 1 just means one more term, the k plus first term. So this would be, instead of writing equals, I'm just going to put a colon there. That would be 2 plus 4 plus 6 plus 8 plus dot 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 plus this one, 2k, and then the next one. So the next one is when the subscript would be k plus 1, so this would be 2 times the k plus 1. Alright, and is this equal to what we would get here if we replace k with k plus 1? Does this equal k plus 1, k plus 1, that's what I plugged in for k, plus the 1. So on the left side, I know from just a minute ago, I stated that this part here is equal to this amount. So I'm going to replace it with k times k plus 1, all of this, then I have plus 2 times the quantity k plus 1. Does that equal here? Now on the right side I can simplify it a little bit. Again, 1 plus 1 coming into play, and that's k plus 2. Well, let's see if this is a true statement. I am going to distribute, simplify. I get k squared plus k plus 2k plus 2. I get like terms, I have k squared plus 3k plus 2. And I have, well, it looks like it's going to factor into a k and a k, a 2 and a 1, looks like a plus 1, a plus 2. And son of a gun, look at that, just like I knew what I was doing. I have a true statement. So that means that this being true implies that this is true, and there's that domino effect. I start with the first one, the second one is true because of the first one, the third one is true because of the second one, and I work my way right down the line. Now, mathematical induction, I didn't see this in high school, so I'm really hoping you take advantage of this exposure to it, because typically in a first year math class in college, there's a pretty good chance that you're going to come across this. Now, the next example, it's a little bit more because it has some rational expressions in there, but we can work this out. We're going to do the same two steps. We'll start off over here that with the first step, that piece of 1. Now, piece of 1 over here, we're trying to show that 1 over, here, let's use a colon here instead of being equal to 1 times 3 plus 1 over 3 times 5 plus 1 over 5 times 7. Notice consecutive, increasingly consecutive odd integers that are being multiplied all the way up to here, and these are consecutive odd because any number you plug in for n, 2 times n is even, minus 1 would make it odd, 2 times n is even, plus 1 would make it the next bigger odd number. And does that equal n over 2n plus 1? Can you see that? I think you can see that, okay? So let's make sure here that it works for the initial statement. Now the initial, the first term here would be 1 over 1 times 3. Does this equal to this when n is 1? Well, when n is 1, I have 1 in the numerator. I have 2 times 1 plus 1 in the denominator. So I have 1/3 is equal to, over here, looks like 3 in the denominator. Checks out okay. Now the next step is usually the one that has a little bit more to it. I'm going to just kind of clear this out a little bit there. And I have now piece of k, which would be, follow this, write this exactly the same except replace the n's with k's. And I have 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 5 times 7. I'm writing a little bit smaller so I can squeeze it in here. Plus 1 over, this would be 2k minus 1 times 2k plus 1. And here's where it gets a little fancy. I need to write the, equal, jump the gun, to k over k, 2 times k plus 1. To find the pk plus 1, it's going to be all this plus the next term. So 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 5 times 7 plus dot 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 plus 1 over the quantity 2k minus 1 times the quantity 2k plus 1 equal, plus one more term plus the k plus first. So that means I have to replace the k in here and in here with k plus 1. Be very careful with this step. It's a little confusing, especially if you're new to this, but this is going to be 2 times k plus 1 minus 1. Oh, tell you what, let's keep that bracket there. Times 2 times k plus 1 plus 1. All right, now extend the fraction bar there a little bit. And now I'm also going to have to replace the k's in here with k plus 1. And I think maybe I have left myself just enough space. 2 times k plus 1, all that plus 1. Yikes. And just like I did in the last example, I have this part, which is right here, and I have assumed that this is equal to k over 2k plus 1. Plus, now I'm going to go ahead and I'm going to simplify the stuff inside the brackets here a little bit to save myself a little bit of work, and that's going to be, this would be 2k plus 2 minus 1 is 2k plus 1, and this is going to be 2k plus 2 distributing plus 1, and this is going to be 2k plus 3. Does that equal, over here, k plus 1 all over, simplifying 2k plus 2 plus 1, 2k plus 3. Well, the only way I'm going to be able to figure this out is if I go ahead and try to combine this and see if I match up on the right side. I need to do the common denominator thing because I'm adding two rationals. So these factors are the same. I need a factor of 2k plus 3. So top and bottom by 2k plus 3. Be careful. Don't make a silly algebra mistake here. So on top here, I'm going to go ahead and distribute. And I have 2k squared plus 3k. And I'm going to go ahead and combine my fractions here because I'm going to have a common denominator. Plus 1 all over my common denominator of 2k plus, let's put the 1 first. 2k plus 1 times 2k plus 3. And again, I'm going to see if this equals k plus 1 over 2k plus 3. A lot of writing here. So this is going to hopefully factor, and it sure looks like it's going to. which is good news for me because I'm never going to make the left side look like the right side unless something cancels top and bottom. Let's see what this factors into here. This is going to be a 2k here, it's going to be a 1k there, 1 and 1. Yeah, if they're both pluses, this is going to work like a dream here. Oh, look at this. Just like I knew what I was doing. K plus 1 all over 2k plus 3 is equal to k plus 1 all over 2k plus 3. Whew. You know, I've been doing these videos now pretty much, this is about my 200th video approximately, and I'm hoping you guys are getting something out of this because as I go around and help you guys, I notice that some of you don't even know where the videos are or what they're on. You know, it gets a little frustrating. It gets to the point where it's like, am I doing this for nothing? Have I done all this hard work and you guys aren't taking advantage of it? It's unbelievable. I just helped somebody today. I didn't know there was a video on this. Man, I'm just about, I don't know, I just about had it.
Hey, Teach, you don't seem like yourself today. Try this.
Oh.
Man, I feel so much better. I don't know what came over me. Back to this math.